Most people think Antarctica is simply an enormous frozen wilderness, a place so cold and remote that almost nothing important could possibly happen there. It appears empty on maps, isolated from everyday life, separated from the rest of the world by thousands of kilometers of some of the roughest oceans on Earth. There are no permanent cities, no highways, no industries on the scale seen across other continents. At first glance, it seems like the last place anyone would need to care about. But that assumption hides one of the greatest misunderstandings of our time. Antarctica may be the quietest continent on Earth, yet it silently influences the lives of every person on the planet, including those who will never come close to seeing its shores. The strange truth is that decisions made in Antarctica can affect food prices, weather patterns, international politics, scientific discoveries, and even the future of global security. Scientists travel across the world to spend months in complete isolation there, enduring darkness, extreme cold, and dangerous storms, not because Antarctica is beautiful, but because it holds answers that exist nowhere else. Every year, governments invest hundreds of millions of dollars to maintain research stations in an environment where simply delivering fuel can become a major logistical operation. Countries continue expanding their scientific presence despite the enormous costs. That raises an obvious question. Why would so many nations compete for access to a place that supposedly has nothing? The answer begins beneath the ice. From space, Antarctica looks like a solid white shield covering nearly the entire continent. Yet that surface conceals a landscape unlike anywhere else on Earth. Massive mountain ranges, valleys deeper than the Grand Canyon, hidden lakes, active volcanoes, and entire ecosystems remain buried under an ice sheet that reaches almost 5 kilometers thick in some places. If all of that ice were suddenly removed, Antarctica would not resemble the flat, frozen desert people imagine. It would reveal a rugged continent shaped by rivers, forests that existed millions of years ago, and geological features that scientists are only beginning to understand. Even more remarkable is the sheer amount of frozen water stored there. Around 90% of the world's ice and roughly 70% of its fresh water are locked inside Antarctica. That single fact gives the continent extraordinary importance. It functions as Earth's largest freshwater reserve, preserving an amount of water so immense that no human engineering project could ever hope to replicate it. As long as that ice remains stable, coastlines around the world remain relatively predictable. But if significant portions begin disappearing faster than nature can replace them, the consequences extend far beyond the polar regions. This is not a distant possibility discussed only in scientific conferences. Satellites constantly monitor Antarctica because researchers have observed changes that were once considered almost impossible. Some glaciers are retreating faster than expected. Ice shelves that survived for thousands of years have fractured within weeks. Warm ocean currents are reaching parts of the continent once protected by colder waters. Every new measurement contributes another piece to a puzzle that scientists still cannot fully solve. Yet climate is only one part of the story. Hidden beneath Antarctica lies something that has attracted attention for decades, but is rarely discussed outside scientific and political circles. Geological surveys suggest the continent may contain enormous reserves of valuable minerals, rare earth elements, oil, and natural gas. No one knows their exact quantity because international agreements currently prohibit commercial extraction. Those treaties transformed Antarctica into a continent dedicated to peace and scientific research rather than economic exploitation. On paper, that sounds like a permanent solution. In reality, international agreements depend on nations continuing to support them. As global demand for strategic resources increases, Antarctica becomes more than a scientific frontier. It becomes a place where future economic interests could collide with environmental protection. Several countries maintain year-round research stations across the continent. Officially, these facilities exist to conduct scientific work. They study weather, biology, astronomy, geology, and climate. Those missions are genuine, but they also establish long-term national presence in one of the least governed places on Earth. History has repeatedly shown that scientific exploration and geopolitical influence often develop side by side. That reality creates an uncomfortable possibility. Antarctica is peaceful today, not because it lacks value, but because the world collectively agreed to keep it that way. The greater its strategic importance becomes, the greater the pressure on that agreement may become in the future. And there is one discovery beneath the Antarctic ice that has forced scientists to rethink almost everything they believed about life in the most extreme environments on Earth. It remained completely hidden for millions of years, sealed away beneath kilometers of ice, untouched by sunlight, isolated from the outside world for longer than human civilization has existed. When researchers finally realized what was waiting below, Antarctica stopped being just the coldest continent on Earth. It became one of the greatest scientific mysteries still unfolding today. The mystery began to deepen in the middle of the 20th century, when advances in radar technology allowed aircraft to see through the ice for the first time. Instead of finding a featureless block of frozen water, researchers discovered something astonishing. Hidden below the ice sheet were hundreds of lakes that had never been exposed to the atmosphere. They had remained sealed beneath kilometers of ice for periods measured not in centuries, but in millions of years. One of them immediately stood out. Known as Lake Vostok, it lies beneath nearly 4 kilometers of solid ice and stretches for more than 250 kilometers, making it one of the largest lakes on Earth, despite being completely invisible from the surface. For decades, scientists debated whether anything could possibly survive in such an environment. There is no sunlight, the pressure is immense, temperatures remain below freezing, and the lake has been isolated from the rest of the planet for an unimaginable span of time. Conventional thinking suggested it should be sterile, yet every attempt to model its chemistry hinted at something different. Minerals rising from the lakebed, geothermal heat from deep within the Earth's crust, and oxygen trapped in ancient ice might have created conditions capable of sustaining microbial life. If organisms had survived there independently for millions of years, they would represent one of the most isolated ecosystems ever discovered. Reaching the lake proved to be one of the greatest engineering challenges in polar exploration. Scientists faced a difficult dilemma. Drilling directly into the water could contaminate an untouched environment that had remained sealed since long before humans evolved. Years of international debate followed before carefully controlled drilling techniques were approved. Every meter of progress required extraordinary precision. Equipment had to function in temperatures capable of freezing hydraulic fluids, damaging electronics, and turning metal brittle. A single mistake could compromise decades of research. When drilling operations finally approached the lake, anticipation spread throughout the scientific community. Laboratories across multiple countries waited for samples that might reveal organisms completely unknown to biology. The first analyses produced unexpected genetic material that did not immediately match known databases. While later studies suggested some of those findings were likely the result of contamination, other microorganisms recovered from surrounding ice appeared genuine, demonstrating that life had indeed persisted under conditions once considered nearly impossible. The exact diversity hidden beneath Antarctica remains uncertain because only a tiny fraction of these subglacial environments has ever been explored. That discovery carried implications far beyond Antarctica itself. If microscopic life can survive beneath kilometers of ice with no access to sunlight, then similar environments elsewhere in the solar system suddenly become much more interesting. Moons such as Europa and Enceladus, both believed to contain oceans beneath frozen surfaces, may no longer seem like impossible places for life to exist. Antarctica has effectively become the closest natural laboratory available for studying worlds that humans have never visited. But hidden lakes are only one chapter in the continent's secrets. Every year, Antarctica quietly records Earth's history with extraordinary precision. Snow falls, compresses into ice, and traps tiny bubbles of ancient atmosphere inside each new layer. Those bubbles preserve actual samples of the air that surrounded the planet hundreds of thousands of years ago. Unlike fossils or rock formations, they contain direct evidence of Earth's past atmosphere. Scientists extract long cylinders of ice called ice cores, some extending more than 3 kilometers below the surface. Each layer represents another page in an archive stretching back through multiple ice ages. By analyzing these frozen records, researchers can reconstruct volcanic eruptions, massive wildfires, ancient temperatures, shifts in greenhouse gases, and even changes in ocean circulation. Events that occurred long before written history remain preserved with remarkable detail. Antarctica does not merely contain clues about the past. It stores one of the most complete environmental records ever found anywhere on Earth, yet that archive is becoming increasingly fragile. Once an ice shelf collapses or a glacier melts into the ocean, portions of that natural record disappear forever. Some locations can never be recovered because the conditions that created them no longer exist. Scientists often describe their work as a race against time, not because they expect Antarctica to vanish, but because certain opportunities for discovery may exist only once. And among all the questions researchers continue asking, one stands above the rest. If Antarctica has already revealed hidden lakes, buried mountain ranges, ancient climate records, and ecosystems isolated for millions of years, what else remains concealed beneath ice that, in many places, humanity has never even reached? Long before satellites orbited the Earth or powerful computers began modeling the planet's climate, Antarctica was already controlling systems that no one could see. Far beneath the constant winds and endless ice, the continent was helping regulate the circulation of the world's oceans. It is easy to imagine the oceans as enormous bodies of water simply pushed by winds and tides, but the reality is far more complex. Invisible rivers flow beneath the surface, transporting heat, oxygen, nutrients, and carbon across entire hemispheres. These currents connect every major ocean into a single global system, and Antarctica sits at one of its most critical control points. Each winter, as sea ice forms around the continent, something remarkable happens. Salt is expelled from the newly forming ice, making the surrounding seawater colder, denser, and heavier. That dense water sinks toward the ocean floor and begins an incredibly slow journey across the planet. Scientists refer to this process as Antarctic bottom water formation. Although it happens thousands of meters below the surface, its influence extends into every ocean basin. Without this constant production of dense water, the global circulation system that helps stabilize Earth's climate would operate very differently. The scale is almost impossible to visualize. Water that sinks near Antarctica may not return to the surface for hundreds or even more than 1,000 years. During that time, it travels across vast underwater landscapes, carrying dissolved oxygen that supports marine ecosystems far from the polar regions. It also stores enormous quantities of carbon absorbed from the atmosphere, effectively acting as one of the planet's largest natural climate regulators. In many ways, Antarctica functions like the hidden engine room of Earth's oceans. Most people never think about it, yet its continuous operation affects weather, fisheries, rainfall, and temperatures across continents. Researchers have become increasingly concerned because recent observations suggest that this engine may be changing. As more freshwater enters the Southern Ocean from melting glaciers and ice shelves, the surrounding seawater becomes less salty. Less salt means lower density. Lower density makes it more difficult for water to sink. Why? If that process weakens significantly over the coming decades, the consequences could ripple through the global ocean circulation in ways scientists are still trying to predict. The challenge is that no laboratory experiment can fully replicate such an immense system. Antarctica is the laboratory. Every research vessel, every underwater sensor, every autonomous robotic float contributes another small piece to understanding a process that spans the entire planet. Some expeditions spend weeks battling storms simply to deploy instruments capable of recording temperatures and salinity deep below the surface. Sometimes those instruments remain underwater for years before transmitting their data. The information they collect often changes scientific understanding in unexpected ways. One surprising discovery emerged when researchers began mapping the ocean beneath floating Antarctic ice shelves. Instead of finding relatively calm water, they detected warm currents reaching deep underneath the ice from directions previously considered unlikely. The water was only a few degrees above freezing, yet that small difference proved sufficient to melt ice from below. Unlike melting at the surface, this process is almost invisible from satellites until major structural changes begin to appear. Entire ice shelves can gradually weaken from underneath, while their upper surfaces seem largely unchanged. That realization fundamentally changed how scientists study Antarctica. It became clear that understanding the continent requires looking not only at the ice above sea level, but also at the hidden interactions occurring hundreds of meters below it. Oceanographers, glaciologists, climatologists, and geologists now work together because no single field can explain the complete picture. The deeper researchers investigate, the more interconnected everything appears. Ocean temperatures influence glaciers. Glaciers influence sea level. Sea level influences coastal communities. Ocean circulation influences rainfall and agriculture thousands of kilometers away. What seems like an isolated frozen continent turns out to be linked to systems that support billions of people. Yet perhaps the most unexpected connection has nothing to do with oceans or climate. It comes from the sky above Antarctica, where scientists once discovered a phenomenon so alarming that it forced governments around the world to take unprecedented action. It also became one of the clearest examples in history of how a discovery made over the Antarctic ice could change the daily lives of nearly every person on Earth. In 1985, a group of British scientists working with data collected above Antarctica announced a discovery that many experts initially struggled to believe. Their instruments showed that the concentration of ozone high in the atmosphere had fallen dramatically over the continent each spring. At first, many assumed the measurements were wrong. The numbers appeared too extreme to be real. Satellites had not clearly identified the same pattern, partly because their software had been programmed to reject readings that seemed physically impossible. What researchers thought were faulty observations turned out to be one of the most significant environmental discoveries of the 20th century. The ozone layer exists high above Earth's surface, absorbing much of the sun's harmful ultraviolet radiation before it reaches the ground. Without it, living organisms would face far greater exposure to radiation capable of damaging DNA, increasing skin cancer rates, harming crops, and disrupting marine ecosystems. Until the Antarctic observations forced scientists to investigate more closely, few realized that human-produced chemicals could alter this protective shield on a global scale. The continent's unique weather conditions made the problem visible there first. During the long Antarctic winter, temperatures in the upper atmosphere fall so low that unusual clouds form high above the ice. These clouds provide ideal surfaces for chemical reactions involving chlorofluorocarbons, commonly known as CFCs. For decades, those compounds had been used in refrigerators, air conditioners, aerosol sprays, and industrial processes around the world because they were considered stable and safe. Ironically, that very stability allowed them to drift into the upper atmosphere, where sunlight eventually released chlorine atoms capable of destroying ozone molecules in enormous numbers. When spring sunlight returned to Antarctica after months of darkness, those chemical reactions accelerated rapidly. Within weeks, a massive region of depleted ozone appeared over the continent. It became known simply as the Antarctic ozone hole, although it was not literally a hole, but an area where ozone concentrations dropped to unusually low levels. Every year, the pattern repeated itself, providing scientists with unmistakable evidence that human activity could alter atmospheric chemistry on a planetary scale. The response that followed remains one of the rare examples of widespread international cooperation driven by scientific evidence. In 1987, nations agreed to phase out many ozone-depleting substances through the Montreal Protocol. Over time, nearly every country joined the agreement. Industries developed safer alternatives, production of the most damaging chemicals declined sharply, and monitoring stations across Antarctica continued measuring the atmosphere year after year. Those measurements have revealed encouraging signs. The ozone layer has shown gradual recovery, although the process is slow because many of the original chemicals remain in the atmosphere for decades. Scientists expect substantial recovery during the second half of the 21st century if current international commitments continue. Antarctica, therefore, became more than a place where a global environmental problem was discovered. It became proof that scientific observation, international cooperation, and long-term policy could successfully address a threat affecting the entire planet. Yet Antarctica continues delivering surprises that challenge existing assumptions. One of the least expected discoveries came not from the ice, the ocean, or the atmosphere, but from outer space. Because the continent is covered by an immense, stable sheet of ice with very little rainfall, vegetation, or erosion, meteorites that land there remain remarkably well preserved. Over thousands of years, flowing glaciers slowly transport these rocks until they accumulate in specific regions, where winds remove surface snow and expose dark stones against bright ice. The contrast makes them surprisingly easy to spot. Today, Antarctica has become one of the world's richest hunting grounds for meteorites. More than 45,000 specimens have been recovered, including fragments originating from the Moon and even Mars. Some of these rocks traveled through space for millions of years before falling to Earth, preserving information about the early solar system that cannot be obtained anywhere else. Each expedition searching for meteorites operates in one of the harshest environments imaginable, knowing that an ordinary-looking stone resting on the ice could completely transform scientific understanding. That possibility captures something fundamental about Antarctica. Again and again, discoveries made there have changed how humanity understands its planet, its atmosphere, its oceans, and even its place in the solar system. But perhaps the most consequential discoveries are not the ones scientists have already made. They may be the ones that remain hidden beneath an ice sheet so vast that humans have directly explored only a tiny fraction of what lies below. If Antarctica were valuable only because of science, international interest in the continent would probably be much smaller than it is today. Yet every year, more countries invest in polar infrastructure, construct new research facilities, modernize airfields, expand logistics networks, and send increasingly sophisticated equipment into one of the most difficult environments on Earth. Officially, these missions are dedicated to peaceful scientific research, and in practice, they produce enormous amounts of valuable knowledge. At the same time, they also reveal a quieter reality. Antarctica has become one of the most strategically significant places on the planet, not because anyone owns it, but because no one truly does. Unlike every other continent, Antarctica has no permanent government, no indigenous population, and no internationally recognized sovereign nation controlling its territory. Instead, its future is guided by the Antarctic Treaty System, an agreement originally signed in 1959 by 12 countries and later joined by many others. The treaty froze territorial disputes, prohibited military activity, banned nuclear explosions, and established the continent as a place devoted primarily to peaceful scientific cooperation. For more than 6 decades, it has remained one of the most successful international agreements ever created. That success, however, depends on something remarkably fragile. It depends on continued cooperation between nations whose relationships outside Antarctica are often defined by intense political rivalry. Several countries maintain territorial claims that overlap with one another. Others, including major global powers, neither recognize nor reject those claims, preserving their own legal positions for the future. While these disagreements rarely attract public attention, they have never completely disappeared. They simply remain suspended under the framework of the treaty. As long as that system functions, Antarctica remains one of the few regions where geopolitical competition is carefully managed rather than openly displayed. Yet global circumstances continue changing. Advances in technology now allow scientists to map areas beneath the ice with extraordinary precision. Satellites measure changes in ice thickness to within centimeters. Aircraft equipped with sophisticated radar reveal hidden mountain ranges and deep sedimentary basins. Autonomous underwater vehicles explore cavities beneath floating ice shelves that humans cannot directly access. Every technological breakthrough increases knowledge of Antarctica's geology, climate, and natural resources. At the same time, it increases awareness of the continent's long-term strategic value. Although commercial mining is prohibited under current international agreements, geological evidence indicates that Antarctica may contain significant deposits of coal, iron ore, copper, rare earth elements, hydrocarbons, and other valuable minerals. The true quantities remain unknown because large-scale exploration is not permitted. In many regions, even confirming their existence would require drilling through kilometers of ice under conditions that remain technically and environmentally challenging. For now, those resources remain untouched, but history offers many examples of places once considered inaccessible eventually becoming economically attractive as technology improved. The Arctic has already experienced growing commercial interest because shrinking sea ice has increased access to shipping routes and natural resources. Antarctica presents a very different environment, yet technological progress continually changes what is considered possible. As engineering advances, questions that once belonged only to science gradually begin entering discussions about economics, international law, and future resource management. This is one reason scientific stations carry importance beyond the research they produce. A permanent presence demonstrates logistical capability, operational experience, and long-term commitment to polar activities. Maintaining year-round operations in Antarctica requires specialized ships, aircraft capable of operating on ice runways, reliable communication systems, advanced medical support, and personnel trained to survive months of isolation. These capabilities cannot be developed overnight. They represent decades of investment. As a result, Antarctica has become a place where scientific achievement and national influence often grow together without directly conflicting. Researchers publish climate studies, biological discoveries, and geological surveys, while governments quietly strengthen their expertise in operating on the frozen continent. Perhaps the most remarkable aspect is that this competition has remained overwhelmingly peaceful. In a world where strategic regions often become sources of confrontation, Antarctica has largely avoided that pattern. Whether that balance continues for another 50 or 100 years depends on political decisions that have not yet been made. But there is another reason nations continue investing in Antarctica, one that has nothing to do with hidden minerals or international treaties. It lies above the ice rather than beneath it, where the continent's unique atmosphere creates conditions unlike anywhere else on Earth, allowing scientists to observe the universe with a clarity that few other places can match. Astronomers often describe Antarctica as one of the closest places on Earth to observing from space without ever leaving the planet. At first, that comparison sounds exaggerated. After all, the continent is covered in snow and ice, battered by relentless winds, and isolated from the rest of civilization. Yet, the same conditions that make Antarctica so hostile for people make it exceptionally valuable for studying the universe. The interior of the continent is one of the driest places on Earth. Although it is covered by ice, very little new snow actually falls each year in many regions. The air contains remarkably small amounts of water vapor, especially during the long Antarctic winter. That detail matters because water vapor absorbs and distorts many wavelengths of light arriving from distant objects in space. In most parts of the world, atmospheric moisture limits what ground-based telescopes can detect. Over Antarctica, those limitations are dramatically reduced. Another advantage is the extraordinary stability of the atmosphere above the Antarctic plateau. Air turbulence, which causes stars to appear to twinkle when viewed from Earth, is often weaker there than at many other observing sites. For astronomers searching for faint signals from distant galaxies or studying the earliest moments of the universe, that stability provides an invaluable scientific advantage. Some telescopes can observe the sky continuously for months without the interruptions caused by the normal day and night cycle, because the sun remains below the horizon throughout the Antarctic winter. That uninterrupted darkness has transformed Antarctica into one of the world's premier locations for certain types of astronomical research. Scientists have installed specialized observatories near the South Pole to investigate the cosmic microwave background, the faint radiation left behind by the Big Bang. Detecting those nearly invisible signals requires instruments operating in extremely cold, stable conditions with minimal atmospheric interference. Antarctica naturally provides exactly that environment. These observations are not simply academic exercises. By measuring tiny variations in ancient radiation, researchers refine estimates of the universe's age, composition, and large-scale structure. They investigate how the first galaxies formed and test fundamental theories of physics that cannot be examined inside ordinary laboratories. In this sense, Antarctica connects two seemingly unrelated frontiers. One lies beneath kilometers of ancient ice. The other extends billions of light years into deep space. The continent also hosts detectors unlike almost anything else on Earth. Buried deep beneath the Antarctic ice is IceCube, one of the largest scientific instruments ever constructed. Rather than observing visible light, it searches for neutrinos, subatomic particles that pass through planets, stars, and entire galaxies with almost no interaction. Every second, trillions of neutrinos pass through the human body unnoticed. Capturing even a tiny fraction of them requires an enormous volume of perfectly transparent material. Antarctica's exceptionally clear ancient ice provided the ideal solution. Thousands of sensitive optical sensors were lowered into holes drilled more than 2 kilometers beneath the surface before the water refroze around them. Together, they monitor an entire cubic kilometer of ice, waiting for the rare flashes of light produced when a neutrino finally interacts with an atomic nucleus. Those brief signals help scientists trace violent events occurring across the universe, including exploding stars, supermassive black holes, and other powerful cosmic phenomena. It is remarkable that one of humanity's most advanced astronomical observatories operates beneath a frozen continent that many people still imagine as empty wilderness. Antarctica demonstrates again that its greatest importance often comes from functions invisible to the casual observer. Yet even as scientists search the universe from Antarctica, another team of researchers focuses on something much closer to home. They monitor the continent itself with increasing urgency because satellite images have begun revealing changes that were almost unimaginable only a generation ago. Some of Antarctica's largest glaciers are no longer behaving as they did throughout recorded history, and what happens next may determine the future shape of coastlines around the world for centuries to come. For most of human history, Antarctica seemed too distant to influence everyday life. It appeared on maps as a blank white mass at the bottom of the world, separated from major population centers by thousands of kilometers of open ocean. That perception is beginning to disappear. Modern satellites, ocean sensors, and decades of field observations have revealed a reality that is far more immediate. Changes taking place on the Antarctic continent are no longer isolated events occurring at the edge of civilization. They are becoming measurable forces that can affect coastlines, economies, infrastructure, and communities across the globe. One of the greatest concerns centers on the vast glaciers of West Antarctica. Unlike many glaciers that rest securely on solid ground above sea level, several of Antarctica's largest glaciers are anchored on bedrock that lies far below the ocean surface. This unusual geography makes them especially vulnerable. Warm ocean water can reach beneath their floating ice shelves, gradually thinning them from below. As those ice shelves weaken, they lose part of their ability to slow the enormous rivers of ice flowing from the continent's interior. The glaciers themselves then begin moving faster toward the sea. Among the most closely monitored is Thwaites Glacier, often referred to by researchers as one of the most important glaciers on Earth. Covering an area roughly comparable to the size of Florida, Thwaites already contributes to global sea level rise through the ice it loses each year. Scientists are concerned not only about its present condition, but also about what could happen if its retreat accelerates beyond certain natural thresholds. Because neighboring glaciers are connected within the same ice sheet, significant changes in one region may eventually influence the stability of others. Understanding exactly how quickly these processes might unfold remains one of the greatest scientific challenges in climate research. Ice sheets do not behave like simple blocks of frozen water. They fracture, flow, melt from below, accumulate snowfall above, interact with ocean currents, and respond to atmospheric changes in ways that vary from one region to another. Even the world's most advanced computer models continue improving as new observations become available. Antarctica constantly reminds scientists that the system is more complex than previously believed. This uncertainty does not mean that researchers lack evidence. On the contrary, modern technology now allows changes to be measured with remarkable precision. Satellites monitor the elevation of the ice surface over time. Radar instruments calculate glacier speeds down to a few meters per year. GPS stations record tiny movements of the underlying bedrock as the immense weight of the ice changes. Aircraft equipped with ice-penetrating radar reveal hidden valleys and mountains buried beneath kilometers of ice. Together, these observations create one of the most detailed environmental monitoring networks ever assembled. One of the most surprising discoveries has been the speed at which some Antarctic glaciers can respond once critical conditions develop. In certain locations, glacier flow has accelerated significantly within just a few decades, demonstrating that the ice sheet is capable of changing more rapidly than earlier generations of scientists assumed. That realization has shifted much of modern polar research toward identifying potential tipping points before they are reached, rather than simply documenting changes after they occur. At the same time, Antarctica remains unpredictable. Some regions have shown periods of relative stability, while others have experienced dramatic transformation. Snowfall can temporarily offset ice losses in specific areas, while neighboring sectors continue thinning. This complexity is precisely why continuous observation is essential. The continent cannot be understood through isolated measurements taken years apart. It must be monitored constantly because even subtle changes may signal larger processes already underway. Perhaps the most remarkable lesson is that Antarctica is teaching scientists not only about its own future, but about Earth's ability to adapt to change. Every expedition, every satellite pass, and every new dataset brings researchers closer to understanding how one frozen continent helps shape the future of an entire planet. Yet there is one final reason Antarctica may be more important than most people realize, and it has less to do with what the continent contains than with what it represents for humanity's future in a rapidly changing world. Perhaps the greatest misconception about Antarctica is that its importance depends entirely on what humanity can extract from it. Throughout history, many regions of the world gained value because they contained fertile land, minerals, forests, or strategic trade routes. Antarctica follows a completely different pattern. Much of its significance comes precisely from the fact that it has remained largely untouched. It is one of the last places on Earth where natural systems still operate on a continental scale with relatively limited direct human disturbance. That makes it something increasingly rare in the modern world, a reference point against which scientists can measure the changing planet itself. Every year, thousands of researchers travel to Antarctica, not because they expect immediate economic returns, but because many of the questions they seek to answer cannot be investigated anywhere else. Ancient ice preserves atmospheric samples stretching back hundreds of thousands of years. Remote mountain ranges reveal geological processes hidden beneath kilometers of frozen terrain. Isolated ecosystems survive in conditions once believed incapable of supporting life. The Southern Ocean records subtle changes in heat distribution that influence climates far beyond the polar regions. Each scientific discovery adds another piece to a puzzle that extends far beyond Antarctica itself. The continent has repeatedly demonstrated that events occurring there often become visible long before similar patterns emerge elsewhere. Scientists first identified the ozone hole over Antarctica. They have documented some of the clearest evidence of changing ice dynamics there. Studies of subglacial lakes have expanded understanding of life in extreme environments. Antarctic research has influenced oceanography, atmospheric science, astrophysics, microbiology, geology, and planetary exploration. Again and again, what begins as a specialized polar investigation eventually reshapes knowledge across multiple scientific disciplines. This role is becoming even more important as technology continues advancing. Modern satellites now orbit Earth with instruments capable of measuring tiny variations in gravity, ice elevation, and ocean height. Artificial intelligence helps process enormous volumes of environmental data collected every day. Autonomous underwater vehicles reach places that divers never could. Aircraft equipped with advanced radar map hidden landscapes buried beneath the ice with astonishing accuracy. Antarctica is gradually revealing secrets that remained inaccessible for millions of years, yet every answer seems to generate even more questions. One striking reality remains unchanged throughout all of these discoveries. Humans have explored only a small fraction of Antarctica in detail. Large regions beneath the ice have never been directly observed. Entire mountain systems remain buried. Vast stretches of the ocean beneath floating ice shelves are still poorly understood. Scientists continue discovering new microorganisms, hidden lakes, and unexpected geological formations. Even in the 21st century, one of Earth's largest continents remains among its least explored. That fact carries an important lesson. Many people assume that humanity has already mapped and understood nearly every corner of the planet. Antarctica quietly proves otherwise. There are still places where genuine exploration continues, where fundamental discoveries remain possible, and where understanding one remote landscape can transform knowledge about the entire Earth. The frozen continent, therefore, represents more than a scientific frontier. It serves as a reminder that the systems supporting modern civilization are deeply interconnected. Weather patterns, sea levels, ocean circulation, atmospheric chemistry, biodiversity, freshwater reserves, and even astronomical research all intersect in ways that few people would expect when looking at a map of the South Pole. Antarctica is not isolated from the rest of the world. It is connected to nearly every process that makes Earth habitable. That is why Antarctica is far more important than most people realize. It is not simply the coldest place on Earth or the largest desert on the planet. It is a continent that stores the past, influences the present, and may determine part of humanity's future. The more scientists uncover beneath its ice and around its shores, the clearer one conclusion becomes. The fate of Antarctica has never belonged only to Antarctica. It has always been inseparable from the fate of the entire planet.